All right, hello everybody. Sounds like you can hear me. Today I have the pleasure of introducing Jim Baker from the sunny state of Colorado. He's an avid skier, a Rackspace employee, and a core Jython developer. And today he'll be speaking to us on a winning strategy with the weakest link, how to use weak references to make your code more robust. After you, Jim.
So thanks. I think there are people out there. I just can't quite see you, but I'm glad to hear the claps. So in any event, some possible questions that you might have coming into this talk are, what exactly are weak references anyway? How do they differ from strong references? When would I use them? Mentioned core developer Jython. I also wrote a book. I do lots of cool things at Rackspace, including work on Jython. I teach principles of programming languages at the University of Colorado at Boulder. So I love all the sort of fun things I get to do. I also, for instance, in that particular class, I teach the functional programming idiom while we're going through formal operational semantics, that sort of thing. So, you can read this. This comes from our documentation. A weak reference to an object is not enough to keep the object alive. When the only remaining references to a referent are weak references, garbage collection is free to destroy the referent and reuse its memory for something else. However, until the object is actually destroyed, the weak reference may return the object even if there are no strong references to it. So if you looked at this, or you looked at the defining PEP on this, this might not be satisfying in terms of understanding what a weak reference is. It was initially proposed in PEP 205. It was implemented in PEP 2.1, which was released 14 years ago. So that's the flip side of it. Shouldn't we be using this if, in fact, it's such a powerful strategy as I try to convince you for the title of this talk? So I'm going to just suggest that we put together a little intuition. All right, so I'm just going to go over to a console, some live demo. Oops, looks like I've already started something here, so I'll just clear it out. I'm using Python 3.4 because it has built-in tab completion, which is super handy. So let's say I wanted to define some class that I'm going to refer to. I'm just going to do a string. Oh, scroll it up. Let's see here. No, that doesn't do what we want. Hold on. We'll start from the top. Better? Okay. So we'll have a class like this. This is because strings in CPython cannot be just weak referenced. We may import from weak reference. Let's just do it the easy way. And we'll say that we have a weak reference set. Okay, so we've created this collection. By its nature, you're going to think, I'm going to have a weak reference to any of its elements, any of its members. Okay, so what does that mean? I'm going to just create one. Let's create a foo object. I was able to add it. I have this set. Let's list it. Wait, where did it go? All right, so the important thing to know is that GC is now possibly going to just, you may see this thing just immediately go away. All right, because the reference counting for that foo object, that myString foo object, went to 0. The weak reference was cleared out, and it moved out of that set. In something like Jython, it would act a little bit differently. It would have to wait for the garbage collector to clear that up. But in CPython, it could be almost immediate, depending on the way references are held. So in order to actually hold on to this, maybe I would have to go and create some, a All right, so I have this A object. I could import sys, do a ref count on that. Oops. I would see that it's actually 3, which is going to be 1 more than it actually is. It's possible that actually there is a FUM that's already out there that's already been imported, and holding that an additional reference to it. If you actually, it's interesting, you can do things like this, like how many references are there to 1? 715 references to 1. What about 0? 579? Even 42 has a lot of references to it. It's only when you go up to like something like this that you would actually see, oh, there's just this one reference apparently outstanding. That's real. All right. So if I then went and added that to my set, sorry, people who are going to not see that. Oops, looks like oops, helps if I do it the right way. And I did list S. Obviously, it's going to hold it because there is something that is holding that reference. If I delete A from the my namespace and I list S again, well, it looks like it possibly is still there. Let's just do import GC. And do that again, and it's gone. All right? So just some simple things that we're adding intuition to. Strong references, including something, a name like that A, could hold that object and prevent it from being removed from that weak set. But if we just added it without any strong reference whatsoever, it could just be immediately cleared out. Okay. Okay. So S will be eventually empty in the context of potentially some garbage collection. So we've built some intuition, and the thing that I want you to just think about is what do we do with weak references in general? It's to prevent memory and resource leaks. We don't want to be holding on to objects unnecessarily. And of course, we know about this in other contexts. So for example, if I just write code like this, I open up some file, and I don't explicitly close it, does it get closed? Well, at system shutdown it would, but not necessarily without going and causing resource exhaustion. Okay? So garbage collection is not magical. It's not going to just say, oh, this is, I know you don't need this. Instead, it's going to work on some principles around how references work. So it doesn't matter if it's reference counting or some variant of mark and sweep, like you see in, say, Java-based Jython or in PyPy, or some combination as we see with CPython, which actually does do a full mark and sweep occasionally. So the GC cannot read your mind. You may be a developer, it cannot do that. It's not sufficient. Now, you can go and do manual clearances. This is very much like as if you were writing C code. You could use try finally, this sort of pattern, right? You can apply some deeper knowledge of your code, or you can do some cleanup by some other scheme. So you may go and use Dunderdell as a finalizer. And especially in conjunction with some explicit ref counting. So for example, socket makefile does do this. All right, so if you are going and creating what appears to be a file object on a socket makefile will do this for you and allow you to return some number of objects. And it's actually used by a number of other primitives in the socket library. As well as tools out there like URL-lib, if I recall correctly. But the problem is that if it doesn't clean up, as I was mentioning earlier, you may get something like this. And who has seen too many open files? Okay, that's why you came to this talk. You wanted to solve your problem. So this implementation is done through a separate ref counting scheme. So socket makefile is trying to do the right thing for you. And if you look at it, it's going and preventing resources leaks along these lines. All right, so I think we've probably seen Dunderdell before. Again, I haven't mentioned weak references yet after that quick demo. You might use the WIF statement with automatic resource management. You should be doing this. So again, no weak references yet. We're keeping it simple. You don't have to be in this talk. But what if an object is a child in a parent-child relation? You have some sort of tree. You need to track its parent. And the parent wants to track its child. You might be doing this, for example, an expat reader. No, you're not doing an expat reader because you no longer use that old legacy stuff. But I think you see the point. It does happen. I'm going to make that example even simpler. Let's implement a doubly linked list with next and previous references. But we'll also add Dunderdell to clean up resources, right? That sounds like a good combination. And we might see this in order dict, which is a great collection in the collections library. So it preserves the order of insertion. You can get that out when you iterate it or you index. And has great performance with the asymptotic performance being the same as regular dicts. And again, it uses this doubly linked list to preserve insertion order. So why is avoiding strong reference cycles so important? Why, again, I'm trying to motivate this weak reference. Well, again, CPython GC usually does ref counting. But a cycle cannot go to 0 in the presence of that cycle. I'm sorry, a cycle cannot go to 0. So in contrast, what we can do with CPython is use its support for weak references. And in that case, it stores a list of containers to be cleared out, including proxies. It's performed when the referred object is deallocated, which occurs when that ref count goes to 0. No waiting on the garbage collector. And we can see that in this code here. So for instance, if I'm deallocating a set, for example, and I always encourage, if you really want to see what's going on, look at the source, Luke. Use the source. So if there's a weak reference list, there is a list of references that are referring to this object. This will be filled in. When this thing is being deallocated, when its ref count goes to 0, this will clear it out. So one thing I didn't tell you is when you add a weak reference to something, we did see it in that one example when I added that as a member. The ref count for that object is not incremented. Another thing that's a little takeaway here is that there are a lot of objects in CPython that are not weak referenceable, and this is because this does add some overhead in terms of adding potentially this extra list. Okay. So why do you want to avoid those strong reference cycles? Well, they have to wait for mark and sweep GC. CPython's GC has unfortunately stopped the world. And if you look at the decision criteria in GC set threshold, even though it's generational, you can see that it's somewhat problematic to just rely on not exhausting, say, files or other expensive resources, even memory. You know, my experience with a garbage collector is that they work well except when they don't. That may be your experience too. Especially around some small object that happens to be pointing to some expensive external resource. Especially, again, with something where you might run out of files. In any event, there was a bug in order dict around this very issue. Now, for 2.7, they removed the Dunderdell. I'll explain why in just a moment. For 3.2, they replaced del with weak references. And for 3.4, using Dunderdell no longer this finalizer no longer means ref cycles are uncollectible garbage, which is why they had to go and do this. So we see in issue 9825, and again, maybe it's just me as a developer here of Python. But I like to read the bugs. I like to see what's going on. And we see in this issue 9825 the reason why. We had to remove dunder-del from the definition of ordered dict because this prevents user-created self-referencing ordered dictionaries from becoming permanently uncollectible GC garbage, and potentially also having strong references to other things, which could be problematic. Don't want uncollectible garbage. So the other thing was that in 3.2, we replaced del with weak refs. And again, there's this further point that we no longer have to worry about uncollectible garbage. So let's look at the implementation of ordered dict. Okay, so what I find interesting about stuff like this is, again, you can go look into the code. This is actually how you might, you would see, for example, this one use of the proxy mechanism. What's nice about proxy, weak reference proxy, is it basically creates a weak reference and does all the work in terms of making it look like the object that it's referencing. So you don't have to go and do additional step, an additional function call in order to go and dereference that weak reference. It sets up root previous to point to this, because now we're going and adding this to that list, and the way this is done is a doubly linked list with the root pointing to the end. After that point, our previous always has a weak referencing the previous item. Our forward link is just a standard link, a standard strong reference. Why would we want to do that? Because if we have weak references on both sides and nothing else is referencing it, we'll see what we saw with that initial example with weak set. The object is simply, potentially is just going to go away at any time. All right. Now, here's some other interesting things. You see that there's the use of slots to minimize overhead. Because you're using slots, you have to go and actually put weak ref in it as one of the slot names. By the way, these are no-op implementations, no-ops in implementations like Jython. I don't know what the case is in PyPy. It's probably very similar. So the crux of this code is simply going and doing this weak reference proxy. And that's really it. We went through so fast there, I'm not certain that registered. There wasn't a lot of work necessary in order to get this with the desired behavior. Okay? All we had to do was come up with this scheme where we recognized that one side of the relationship, we were going to go and use a strong reference. Arbitrarily, we just simply used the next reference as a strong reference. On the flip side, we wanted to go and make certain that there wasn't a reference cycle. Well, that was easy enough to do. The previous would be a weak reference. Combine those two together, and now we don't have the scenario where this removing an item from this ordered dictionary might take some time for it to be removed just because we have this garbage, or even worse, uncollectible garbage. All right, so that's some motivation, but the reality is we're not normally writing ordered dict. We're going to be doing things like a lookup table, where we're going to want to provide more information about some object. We don't want to extend or monkey patch it. So for those of you who like doing this, and I understand why, you're like, hey, there's this fantastic little dunder dict around for this object, and I'll just name something with, put it in there, and there won't be any collision, or we'll even add it to the class, and there won't be any collision because I'm just adding methods to it. So who has done that? Who's monkey patched or used underdict in this way? No one? Really? You're not fessing up. No, you've already are using this mechanism, right? So you could use a dictionary as this lookup table, where you use the object as a key, but now you need to manually clean up that dict when the object is no longer needed. And maybe you know when it needs to be cleaned up, or maybe you don't because you're doing it in the context of some library. So it's especially useful for libraries. We can use a weak key dictionary. Very similar sort of idea that we saw with the ordered dict. One side is going to be weak, and the other has a strong reference. In this particular case, it's the key that is weak. We insert the object as the key. We can associate anything we want as the value, a list of properties, some other object, so on and so forth. When the object is removed, it goes away because it's no longer in use somewhere else. Nothing else is holding a strong reference to it. Now, the cleanup of that dictionary will occur. Okay? So that key, the item for that key will be removed. And if there's nothing holding on to those associated values in, say, that lookup table, that will also be cleaned up. So we have a lookup table that works the way we want it. The object is gone. These interesting additional properties that we were associating with it are gone now as well, because nothing else is holding on to it. So let's look at one example, Django signals. So Django includes this signal dispatcher. It allows for decoupled applications to get notified when actions occur elsewhere in the framework. This is exactly the sort of thing where you don't know in advance necessarily who's talking to you. The reality, it looks like I got a little bit cut off here, is that it's really just a couple lines to do this setup. You have to still set up what that cache is, but the choice of using a weak key dictionary here is just a couple lines, where really the only extra line here is, are we using caching or not? And if we're not using caching, we'll just have this empty dictionary that we won't use at all, just to have something as a placeholder. And so that's pretty useful. But then you look at the WeakValueDictionary, and you wonder, well, what is that good for? Why is that there? So if you go and do some text search in the standard library, or go out to PyPy, do something similar, you'll see it being used in a number of places. It's being used by multiprocessing, by the logging module, so on and so forth. But again, why weak values? Well, it's useful when you want to track the object by some ID, its name, a number in some table, its process ID. Okay? But you don't want the fact that you have a process ID to a process mapping to not support garbage collecting that process. I mean, yes, the expensive resource is going to go away in the case of a process, but you're still holding on to it unnecessarily. All right. So maybe there is some operating system cleanup that you can do or expect, but again, not always. All right. So once that object is gone, once we no longer need to hold on to that weak value, it's going to go away. Now, interestingly enough, while that object is around, you're going to be holding on to that small integer or string, but generally we discount that. One place that might happen is if you start up lots and lots of threads, and you may just see that, those, I'm not going to see those threads, IDs go away until that particular thread itself is no longer dereferenced. Or no longer reference, rather. Okay, so here's a little bit of guidance in terms of thinking about why you might go and use a weak reference in one place or another. And it's really the consideration of what is the object lifecycle independence. So one side may depend on the other, but not vice versa. So you're going to use weak references for the independent side. The process is terminated. Well, you no longer need to look it up by process ID. It no longer matters, right? Select a weak value dictionary. All right. Could you combine both ideas together? Well, yeah, both sides could be independent. So Jython implements this variant of the Highlander pattern. You want to map the Java class to its Python wrappers, including for support for subclassing that Java class. You may be, that Python class may be used by Java classes. So again, there will be, Python classes to any using Java class, so there will be some strong reference from that Python code. So in both cases, you may have strong references, but the fact that there is this mapping, this one-to-one mapping, you just want to ensure that there can only be one. And when either side goes away, it should also go at that point. So you don't unnecessarily hold on to some resource and leak. So either might go away. The Java classes in this particular case will be garbage collected if no class loader or the objects of that class exist. But the Python usage of this class will be GC'd if there's no usage on the Python side. So you don't want that mapping to unnecessarily hold things. If they are still in use, you want it to be held. But if they go away, then there's no point for this mapping at that point. There's a pure Python recipe available for this. I haven't really evaluated this. There's an easy Jython version, which I'll show because I like to show off Jython occasionally. And here we have it. We have a weak key value dictionary. Its subclass is dict, so we can get its capabilities. We use a builder. Oh gosh, I didn't check this one piece, but it really is just args and keyword args. For completeness, you just need to add these methods, but those are trivial. And then there is a thing in the Jython lib module that you can import that allows you to build dictionaries with any Java compatible concurrent map that you want and assign it to being of a certain class, this weak key value dictionary, and you're done. And now you have a weak key value dictionary for real that is concurrent and safe. And I am done. Any questions?
If there are any questions for Jim, there's a microphone right there. We have time for one question probably. Otherwise, I'm sure you'll be able to grab him out in the hall right afterwards.
Right.
All right, thank you.
Thank you very much.